Okay, so question 1 looks at the currents flowing into a junction. Now, Kirchhoff's current law basically looks at the current into a junction must equal the current out of the junction. So, if I was to, you've got to look at the sign here. We've got 2.3 amps going in to this junction. We've got 1.2 coming in as well. So, the total current coming in must be the total current coming out. So a number of you will probably sort of think that 1.2 plus something is going to give 2.3. But in actual fact, we've got 3.5, so current in, (3.5 amps. Right, I'm going to keep going. Okay, so current in is 3.5 amps, so the current out must also be 3.5 amps. Okay, question 2. In the following circuit, the current through the ammeter A1 is 0.5 amps. Well, let's have a look at what happens with the current. If we have a current coming through this way, this has to be all of the current. This is all of the current. And then what happens is, through a parallel, we're going to have some current, we'll call this I1, going through here, and we're going to have I2 going through here. Now, these don't have to be the same. I1 does not equal I2. The only time when the current through 1 and 2 is going to be the same is when they have the same resistance. Now, with the voltage though, V1 does equal V2 because it's a parallel arrangement. So, voltage through this parallel circuit is the same for each of these, and the current though is not. What is the current through A2? So first of all, we know what the current, it says here that the resistors are equal value. So if they're equal value, then we know that the current through 1 is going to be equal to the current through 2. You don't need to know any values. But in this case, because we know that we've got 0.5 amps, we know that that current's going to split off and we're going to get 0.25 amps for each of those. The current of 1.5 amperes is measured flowing through a different ammeter. How much charge passes through this ammeter in 1.5 minutes? Well, we need to use this relationship. The current is the rate at which the rate of charge. So if we have 1.5 amps, then that is a amount of charge over, and 1.5 minutes, we'd have to convert that to seconds, so we've got 90 seconds. So therefore the charge, and this is obviously in coulombs, so therefore the charge is equal to 90 times 1.5, which is 135 coulombs. Seems like a lot of coulombs. Okay, the next one. In the following circuit, the ammeter is reading 1.25 amps and the voltmeter is 3.75 volts. What is the magnitude of the resistance of the circuit? Well, we have to use that law, so we've got V equals I times R. And total resistance. We can use this Ohm's law as well to find the voltage drop across if we had more than one resistor. So we know that the resistance is therefore E divided by I. The voltage is 3.75 volts and the current is 1.25 amps. So the resistance is going to be 3 ohms. What is the voltage supplied by the battery? Well, it appears as though there's no, all of that voltage that is supplied by the battery is going directly through that resistor. So it appears as though the voltage supplied by the battery is 3 volts. Quite a simple question, really. Question 6. What single resistor could replace the following 3 resistor combination? So first of all, we can draw this an equivalent circuit is the equivalent of basically having one resistor in series to a 4 in series with a 4 ohm resistor. Okay, so this side is quite easy to work out, but we need to find an equivalent resistance of this arrangement here. Now, if I go to and scroll through to the end, let me just go through the end and show you. We need to use this here. So for resistance in parallel, we have each resistance, the power of -1 or 1 over that. So R1 to the power of -1 equal to 1 over R1. So I'd like to write it like this. So the equivalent resistance, we had 2 resistors in parallel, 1 and 2. This is 1, this is 2. To find the equivalent resistance of those, we would 1 over 2, 1 over resistance of 1 plus 1 over resistance of 2, which is this R to the -1. That's what those are. To the power of -1. And if you put that in your calculator, you can find it out. Now, there's a few things that will help you in doing these calculations, and that's, first of all, if you have resistors in parallel, there is no way you can have a resistance higher than a large resistor. It's always going to be lower. If you have 2 resistors of the same resistance in parallel, they're going to be exactly half of the resistance. So I can tell you automatically, because I've actually, I guess, know these principles, is that 2 4-ohm resistors, without even doing any calculations, is going to be 2 ohms. Now, if I had 3 4-ohm resistors, 3 4-ohm resistors, and I could also tell you that it's going to be this 4 divided by 3. Or, if we do it long ways, we're going to have 1 over 4 plus 1 over 4 plus 1 over 4 to the power of -1. Well, 1 over 4, 3 times, is 3 over 4. The -1 just means that we're switching these signs around. So that's going to be 4 over 3. So you can have obviously more than 2. In this case, though, the equivalent resistance of this section is 2 ohms. How can we do it long ways? 1 over 4 plus 1 over 4 to the power of -1, which is equal to 2 over 4 power of -1, which is equal to 4 over 2, or just 2. So what single resistor could replace the following 3 resistor combination? You have a 2 ohm resistor in series with a 2 ohm resistor, so it's going to be 4 ohms. Moving on, question 7-8 refers to the following. Well, we've just done that question, so I'm not sure why that's a repeat. But I'm pretty sure with this one, they're making the assumption that this is just a wire which has no resistance. So what single resistor could replace this would be simply just a 4 ohm resistor. Because quite clearly electricity is going to take this path, and it's certainly not going to, there might be some electrons going through here, but virtually none. So it'll be a negligible amount. So it's still going to go through here. So 4 ohms. What is the name of the direct path from A to B? Well, I guess you'd short circuit. Path of no resistance. Question 9 and 10. thermistor has the following resistance temperature characteristic. Now, a thermistor, like a few other things, so we've got a thermistor, we've got a diode. They don't follow the common sort of ohmic voltage relationship. So if we have a current, an ohmic device will follow a straight line, whereas these certainly don't. They can have all relationships such as this. This is looking at temperature and resistance, but so let's have a look at what the question's asking us. The thermistor is placed in the following circuit. What current flows through the ammeter when the temperature is 50 degrees Celsius? So in order to do that, we need to look at the graph. And we've done this in a couple of the Year 12 questions as well that we looked at. So on the graph, it looks to me that at 50 degrees, the resistance is 30 ohms. So 30 ohms, this is going to be 30 ohms for the time being. So what current flows? So what happens is, as the temperature increases, decreases, the resistance of this thermistor changes, and that increases or decreases the resistance of this total circuit. Now, at this stage, we're going to have a resistance total of 72 ohms, and we have, now what happens is the resistance can change. The voltage supplied by the circuit is always going to be the same, which is 18 volts. And then since the voltage is proportional to the resistance, then the only thing that's really changing is this current. So I is V over R. So as the resistance changes, so does the current. So what current flows through the ammeter when the temperature is 50 degrees? Well, I is equal to V over R. We know our voltage is 18, and our resistance, looking at this diagram, is 30 plus 42, 72, and it's going to be 0.5 amps. The thermistor is considered to be a non-ohmic device. Explain what is meant by the term non-ohmic in this context. Well, it does not follow Ohm's law. There is not a linear relationship between voltage and current. So if we were to look back up here, we're going to say the voltage is proportional to the resistance, and obviously voltage is proportional to the current. Well, it is proportional to the current for this, but it's not a linear relationship. So it's not a steady, if you double the current, you double the voltage, and so on. So when looking at non-ohmic devices, they do not have a linear relationship. Question 11 to 13, a student is studying for exams in the cold winter months. She uses a 1200 watt single bar radiator to keep her warm. So let's write down what we know for starters. P for power is equal to 1200 watts. She studies 3 hours per night, so time is 3 hours per night, 5 days a week. For 4 weeks. So we need to work out the kilowatts of hours of energy she used. So let's have a look at what kilowatt hours is. Okay, so a kilowatt hour is first of all, if we look at in terms of energy, energy is power times time. So where do we get this from? Power is the rate at which the energy is consumed. So let's have a look at the energy is power. So we have power of 1,200 watts times the time, which is, well, we've got to work out, we've got 3 hours times 5 nights times 4 weeks, so that's 20, so that's 60 hours, which is equal to, times that by 3,600 is going to give us seconds. I'm going to do this in my head. 6 times 36 is 200, and 6 times 30 is 1,800, 180. 6 times 6, 36. So it's going to be 216,000. I urge you to use a calculator for these. So we've got 216,000 seconds. Now, if I've got, I'm going to do this without using a calculator. 21, 1, 2, 3, 4. So I've got 21.6 by 10 to the power of 4 times 1.2 by 10 to the 3. So guys, what's 21.6 times 1.2 in your calculator, please? Sorry? 21.6 times 1.2. So we've got 25.92. Okay, cool. And we've got by 10 to the power of 7. So this is in joules. Now, a kilowatt hour is a certain amount of joules. It's basically one megajoule. 1 megajoule, if I was to, where is it? Just trying to find it. So 1 kilowatt hour is 3.6 megajoules. So we have, if we were to divide this by, each one of these is a megajoule. So 25.92. So we've got 259.2 megajoules. Now, each one, if we were to divide that by 3.6, we're going to have the term in kilowatt hours. So divide that by 259.2 divided by 3.6. Someone do that? 259.2 divided by 3.6. Someone. 72. Okay, so the answer is 72 kilowatt hours. So just using this power as energy on time, and there's a conversion. We've got 3.6 megajoules is equal to 1 kilowatt hour. A lot of students struggle with those conversions. Convert one night's kilowatt hours into joules. Well, how many nights have we got? We've got 20 nights. 20 nights. So that means that each night we've got to have 3.6 kilowatt hours each night. And we want to convert that back into joules. Well, each kilowatt hour is 3.6 megajoules. So 3.6 times 3.6 by 10 to the 6 joules. So if we were to do that in our calculators, just work that out. So we've got 12.96 megajoules, or 12.96 by 10 to the 6 joules. Electricity company charges 15 cents per kilowatt hour. How much does the radiator cost to run for 1 week? Well, each day it's going to cost, it's 3.6 kilowatt hours. So in 1 week, we've got 5 days in this week, I believe it was. So 5 times 3.6, which is equal to 21 kilowatt hours. So we've got 21 kilowatt hours, and we then multiply that. So the cost is equal to 21 times 0.15, which is equal to $3.15. $3.15. Okay, so the last question, the following circuit diagram shows 3 resistor combination with some unknown values. And now in your SAC, you'll have a lot of questions similar to this, and you need to know how the voltage and current changes throughout a circuit. So in order to find what is the size of the current flowing through the ammeter, first of all, you really need to know the total voltage of the circuit. Now, given that so in this question we can see that we can use we've given a voltage across here. So let's just call this number 2 and number 1. So the voltage across 2 is equal to 6, and that equals the current across 2, because you know it's going to split out. It's going to some current is going to go here, some current is going to go down this way. So the voltage across 2 is 6, and the current, the resistance across 2 is equal to 3 ohms. So we've got 6 volts across there is equal to current across 2 times 3. So the current across 2 is then therefore going to be equal to 2 amps. So what's happening is we've got 2 amps going through this way, and then that will then go through, we know that 2 amps is going to go through here, and then 2 amps is going to go this way, and we know that the current, we've got 4 amps coming through here, so we know that the current in is equal to the current out. The total current, therefore, is equal to 6 amps. So we've got more current flowing through here and then here. So naturally we would sort of assume that this resistance is actually going to be lower. What is the size of the resistance R? So okay, so looking at this question, guys, looking at this question, we can see that the voltage, we can actually work out the voltage across here. Now, if we work out the voltage across here, it's going to give us the total voltage as well across this side of the circuit, because obviously this is a parallel arrangement, but we have 2 resistors in series. These 2 resistors are in series, and they're in parallel with this. So what we do know is that if we work out the voltage across here, then that voltage across here is going to be the total voltage across here. So this section, the voltage, has to be equal to this section because they are in parallel. This is where a few students get confused. So the voltage across this 6 ohm resistor, voltage is equal to current times the resistance, which is equal to 4 times 6, which is equal to 24 volts. Now, therefore, basically, if we were to do this as an equivalent, we've got 24 volts across here, and therefore we've also got this resistor here, which was 3 ohms, and there was 6 volts across that. So we know that this whole arrangement here needs to be a total of 24 volts because parallel we have the same voltage across them. So that means that this resistor here has to have 18 volts across it. So we know that the current flowing through, we've worked that out in question 14, is 2 amps. And we know that the voltage across this resistor is equal to 18. So therefore the resistance is equal to 9 ohms. So let's have a look at this circuit. We've basically got 6 amps in total, in which 4 amps splits this way, 2 amps splits this way. This 2 amps then goes, we have a 6 volts drop through this resistor, which is of 3 ohms, and naturally we're going to have a higher voltage drop. Since this resistor here is 9 ohms, then that is going to be 3 times the voltage goes through here. So 18 volts drop across there. Then they meet up here, in which we've got 4 amps meet up with 2 amps for our total of 6. So the voltage, the current in, is equal to the current out. And the resistance is 9 ohms. That's a tricky question. That will probably be the hardest one on the exam. What is the size of the voltage supplied by the battery? Well, we've just worked that out before, haven't we? Because we've worked out that the voltage across this parallel circuit is 24 volts there. So therefore the voltage across the battery is equal to 24 volts. And that's it.